Welcome to Analog Electronic Circuits NPTEL course. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. So, we are continuing this topic of common source amplifier, and what we are planning to do it is we have done the analysis, and today we will be covering some of the design guidelines, how we have to select values of different components. So, our plan today it is so, the concepts we are going to cover here today is the guidelines of common source amplifier design, and we will be going through numerical exercise. Through that exercise, we will know that how to select the value of the resistors, maybe capacitors also some extent. Now, so far what we have covered is the analysis. So, what we have done it is suppose we do have this common source amplifier, and then in case the device components or the device parameters are given to us, namely K into W by L, and then threshold voltage of the transistor if it is given, and also the supply voltage is given to us. In addition to that, if the values of R1, R2 and RDs are given, then what we have seen is that how to calculate the gain of the circuit, how to calculate the input resistance of the circuit, those things we have discussed. And also we have seen the sequence of those calculation, namely we have started with DC operating point, namely DC voltage at the gate node, and then followed by calculating the IDS, which is of course function of the parameter here, and the gate to source voltage minus VTH. From that, then we have calculated GM, then voltage gain, and so and so. So, whatever the things we have done and the procedure we have followed, it is referred as the circuit analysis. You may say that it is theoretical analysis or numerical analysis. Today, we are going to discuss the reverse process, namely in case the circuit is given to us and the circuit topology is given to us along with the device parameters and the supply voltage is given to us, and we need to find the values of these resistors, namely the bias resistors R1, R2, then RD, and the values of those components should be such that we should be getting meaningful operation of the circuit, namely at the output we should be having good signal swing, and to achieve that what may be the voltage here we like to obtain, and then to get that DC voltage at the gate what may be the ratio of R1 and R2, those things will do. So, as I said that the main focus of today's discussion is primarily to find rather to how to select the value of different bias components. So, let me go to the next slide where we do have the problem defined. As I said that here the circuit topology is given to us, and what we need to do it is the circuit topology is given to us and the value of these device parameters are given to us. The supply voltage it is given to us, and we need to find the value of resistors and capacitors. The value of the capacitors may be obtained whenever we will be talking about frequency response, but primarily we will be finding the method or procedure to find the values of the resistors. Now, how do you start? First of all, of course, while we will be keeping the circuit in appropriate region of operation, namely the transistor should be in saturation region, and also the DC voltage at the drain should be such that whenever we do have signal. So, along with the DC we are expecting some signal will be there. So, whenever the signal it will be coming here, even if the signal is having good swing, the transistor should remain in saturation region, namely the gate voltage and drain voltage condition should be such that the pinch off it is remaining there. So, if you consider that, then you may say that the for a given VGS voltage. So, if I say that we do have some VGS, and then that VGS minus VTH is the lower limit of the drain voltage. So, if you see the output voltage, its range of the output voltage, in one side we do have the lower side we do have VGS minus VTH, and on the other hand higher side it is of course the supply voltage VDD. And so, we may keep equality also, but maybe we can at least we can say that the output voltage should be lying well within this one. And so, for meaningful operation we want both the positive swing as well as the negative swing may be equal, and hence we like to keep the DC voltage at the drain such that we should be getting both positive side as well as the negative side equal, means the VDS should be middle of these two voltages. In other words, if I take the average of these two voltages, so that gives the DC voltage, and if we do so, if the DC voltage it is set at the average of these two, then we can get the positive side swing and negative side swing, it will be equal, and at the limiting case the swing it will be VDD minus VGS minus VTH by 2. So, I should say the upper limit, pictorially the upper limit here it is VDD, on the other hand lower limit it is VGS minus VTH, and if we are setting the DC operating point at the middle of this. So, we can say whatever the total swing we do have divided by 2 will be the output swing. So, obviously, we want this swing should be as high as possible, and this is the limit. So, if the DC operating point it is skewed towards the VDD, of course, positive side swing it will be less. On the other hand, if it is coming on the lower side, the negative side it will be less. So, the practically what we should try is that the DC operating point we should set to this value. So, that is the first guidelines, and then second one is the voltage gain. So, once we obtain the gate voltage, probably from that we can find what is the corresponding IDS. So, this is IDS versus VGS characteristic curve. So, as we have discussed before, once we fix this operating point, with respect to that operating point we can say that slope of this line is the GM. So, that GM multiplied by RD, that is the gain of the circuit. In fact, if you replace this GM by its expression earlier we have discussed, which is 2 times IDS divided by VGS minus VTH. So, that gives us the gain. So, then where do we start from? In case the device parameter is given to us, and then also we are expecting that the device, the current range of the device may be given to us. That means, the current should be maybe somewhere in maybe sub milliampere to maybe 10 milliamperes or so. So, based on that we may decide to use some IDS value, and from that using this parameter, particularly k into W by L and VTH, we can calculate what is supposed to be the value of this VGS minus VTH, and then that will be helping us to find what will be the value of R1 and R2. So, let us see how we proceed, and as I said that we will start with with IDS, and then we will be subsequently following the steps. So, yes, so let we start that process. Yeah. So, what we have here it is, just to start with as an example, let you consider that IDS equals to 0.5 milliampere. So, if 0.5 milliampere IDS is our target, which means that we can follow the IDS versus VGS characteristic curve, and so this IDS versus VGS characteristic curve. In fact, this characteristic curve equation we already know, namely IDS equals to k by 2 W by L into VGS minus VTH square, and then we do have 1 plus lambda VDS part, that maybe we can ignore. So, approximately you can say that this is approximately 1. So, you may drop this part. So, since this parameter and this parameter is given to us, and also we do have a target value. So, from that we can simply find what will be the corresponding VGS. In fact, if you use this equation, namely 0.5 milliampere equals to 1 milliampere per volt square by 2, then VGS minus VTH square. So, that gives us VGS minus VTH equals to 1 volt, or VGS equals to VTH plus 1 volt. So, this 1 volt normally it is referred as overdrive voltage del VGS. So, the VGS equals to the VTH, which is coming from the parameter given to us 1 volt, and VGS minus VTH, which is we obtained that it is 1 volt. So, that means to obtain this 1 milliampere of current, we need this VGS should be 2 volt. Now, that 2 volt we are generating from 12 volt supply by using this R1 and R2. So, we can say that we can use this equation VGS equals to VDD multiplied by R2 divided by R1 plus R2. So, from this we can say that R2 divided by R1 plus R2 equals to 12. So, this is 2 volt divided by 12 volt, right. So, we do have essentially 1 by 6, or we can say that, so this gives us R1 equals to 5 times of R2. So, this is one relationship. So, we can say that R1 equals to 5 times of R2. So, we obtain the ratio of R1 and R2, but we need absolute value of R1 and R2. So, how do you find? This is again it is just a guidelines, it is not necessary. that this bias current we may take almost 10% of this IDS. So, we can say that I bias equals to 0.1 times IDS, and this current, since the DC current to the gate is 0. So, we can simply say that this I bias is equals to 12 volt divided by R 1 plus R 2. So, that gives us R 1 plus R 2 equals to 12 divided by 0.05 kilo. So, that means it is how much? 240 kilo ohms. So, now I do have R 1 plus R 2 equals to 240 kilo ohm, and also we do have R 1 equals to 5 times of R 2, which means that R 2 equals to 40 kilo ohm, and then R 1 equals to 200 kilo ohm. So, to achieve this 2 volt, or to be more precise, to achieve this target current, we can directly use this R 1 and R 2. In fact, you may find some other solution in case if you are looking for different bias current, but this is one meaningful solution, and we want this current should be maybe smaller because power dissipation, of course. And on the other hand, in case if this current is higher, which means that R 1 and R 2 if they are smaller, then the lower cutoff frequency which will be coming from the C 1 and input resistance, which is essentially R 1 parallel R 2, that lower cutoff frequency it may get affected, namely it may go towards the mid range of the amplifier, right. So, what do you obtain here? It is the value of this R 1 and R 2, namely R 1 equals to 200 K and R 2 equals to 40 K. Now, we need to find what will be the corresponding meaningful value of this R D. So, in the next slide, we will be discussing about how to find this R D. So, of course, we this is our target. Yeah. So, how do we proceed to find R D? First of all, as I said that for IDS equals to 0.5 milliampere, VGS we obtained. Now, the VGS, the voltage here it is 2 volt, threshold voltage it is 1 volt. So, the lowest possible voltage here it is and the voltage here it should be 1 volt. So, this is the lowest possible value. Then higher side we do have the 12 volt. So, to get the maximum swing we should target this quiescent point at the drain node should be middle of these two, and that will be giving us the maximum swing. So, the maximum output swing which we already have discussed that VDD minus VGS minus VTH. So, this is the lower limit by 2. To obtain this maximum output swing, what we can do? We can target this quiescent voltage to be half of this 2 limit. In other words, this IR drop, namely RD into IDS should be such that this voltage it will be middle of these 2. In fact, if you consider that RD multiplied by IDS, so in fact, I should write that the output quiescent point is rather VDD minus RD into IDS, and this is what we are targeting equals to middle of these 2 limit, namely VDD minus VGS minus VTH by 2 right. So, this is our target to get the maximum swing of this one, and from that if we rearrange this equation, what we can get here, it is I R D equals to V D D. So, from this equation we can get R D equals to V D D minus V G S minus V T H by 2 times of I D S. In fact, this is simple. We simply take the I D S here, and whatever the drop we are getting, it should match with this part. And so, that gives us the corresponding value of R D. So, let us see what is the value we are getting using this equation. V D D we do have 12 volt. So, 12 minus V G S minus V T H, that is 1 volt, and then divided by 2 into 0.5 milliampere. So, that gives us 11 kilo ohms. So, this R D we obtain this one. So, now we obtain this R D, R 1 and R 2. So, with this bias or with this design, let us see what is the performance we are getting. So, so the performance with whatever the design just now we obtained, namely the R 1 equals to 200 K, and then R 2 equals to 40 K, and R D equals to 11 K. What are the performances matrices we are getting? First of all, the output swing V D D minus V G S minus V T H by 2, which is actually 11 by 2, that means 5.5 volt. The possible swing here, it is actually plus minus 5.5 volt, right. And the corresponding gain what we can get is G M into R D. In fact, we can write the expression of the G M in terms of I D S and V G S minus V T H. So, which is given here, this is the G M part. So, in this design what we have, it is 2 into I D S is 0.5, and then V G S minus V T H is 1 volt, and of course, this is milliampere multiplied by 11 kilo ohm. So, that gives us the gain of 11. So, this is one performance parameter, and this is also another one. In addition to that, input and output resistances of the amplifier. So, the input resistance in this case, the input impedance of the MOS transistor gate, it is, you may approximate, it is very high. So, we can say that R in, it is primarily coming from the bias circuit R 1 and R 2, or to be more precise, this is R 1 parallel R 2, and this is 40 multiplied by 200 divided by 240. So, that gives us 100 divided by 3. So, that means around 33.3 kilo ohm. So, that is the input resistance, and the output resistance, it is of course, this is we are ignoring this lambda. So, lower side the impedance coming from the transistor, it is, we may say, it is very high. So, output resistance on the other hand, it is R D, which is 11 K. So, to summarize, we are getting the performance of the circuit is the output swing, gain, then input resistance, and then output resistance. So, this is here, of course, so we are starting with I D S is equal to 0.5. Maybe you can work out yourself by targeting maybe different current, and let us see what may be the possible. Yeah. So, in case instead of considering current 0.5 milliampere, now if you say target current of maybe 2 milliampere. So, what kind of changes are happening here? First of all, if you follow the same procedure, VGS minus VTH with this target, VGS minus VTH you will be obtaining equals to 2 volt, and then VGS actually it is 3 volt. So, to get this VGS 3 volt from 12 volt supply, what we will be getting here, it is R 1 by R 2 equals to we do have 12 volt, we like to get 3 volt. So, drop across this one is 9 volt, drop across this R 2 it is 3 volt. So, the ratio here it is actually 3 by 1, or R 1 equals to 3 R 2. And then again if we target say bias current, it is just 10% of this IDS. So, from that we can say that so this is 0.2 milliampere, and VDD is 12 volt. So, that gives us R 1 plus R 2, R 1 plus R 2 equals to 60 kilo ohm, and in addition to that we do have R 1 equals to 3 times of R 2. So, if I combined these two, what we will be getting here, it is R 2 equals to 15 K, and R 1 equals to 45 K, right. So, that is the value of R 1 and R 2. You may recall that we obtained different value of this R 1 and R 2 while you are targeting 0.5 milliampere. Now, next thing is that we can find what will be the corresponding R D. Probably I do have another slide for that. Yeah. So, once we obtain the VGS equals to 3 volt with R 1 equals to 45 K and R 2 equals to 15 K. Then R D, to get the maximum swing, what you have to do that, and this is the maximum swing, the corresponding R D it becomes 12 volt VDD minus VGS minus VTH is 2 now, divided by 2 into 2 milliampere. So, that gives us sorry, this is 10 volt. So, this is 10 divided by 4, 2.5 kilo ohms. So, now you can see the change. Earlier R D it was 11 K kilo ohms, now it is 2.5 kilo ohm, and the voltage here it is 3 volt, and so the lower limit of this voltage here it is 2 volt. This is supply voltage is 12 volt. So, our target voltage here it is 12 minus 2. So, the upper and lower limit if I see. So, we like to place it at the middle of 12 volt and 2 volt, which means that the average of that it is 7 volt, and the drop across this resistance to get this DC voltage of 7 volt. So, here we require 5 volt and 2 milliampere of current is flowing, and hence 2.5 kilo ohm will be giving us the drop across this R D equal to 5 volt. So, that gives us the RD, and the performance of this circuit, in fact, we already have discussed in our analysis part, where we said that the current it was 2 milliampere, right. And once of course, then performance wise, I guess I do have another slide for that, but let me see. Now, let me here itself I can write the other information, namely with this values of R1, R2 and RD, the gain, the voltage gain equals to GM into RD. So, that is 2 times IDS divided by VGS minus VTH into RD. So, we do have 2 into 2 milliampere into 2.5 K divided by VGS minus VTH is 2. So, that gives us a gain of 5. So, earlier we are getting a gain of 11, now we are getting gain of 5. And the input resistance on the other hand, let me use different color. So, input resistance on the other hand, it is R1 parallel R2. So, that is 15 multiplied by 45 divided by 60. So, that is 45 divided by 4. So, that is equal to 11 point whatever 25, and the output resistance of course, the same thing. So, this is the output resistance. So, that is the guidelines to design common source amplifier to get good swing, meaningful gain and so and so. Yeah, so, what are the things we have covered here? It is basically from the device parameter and the supply voltage information, and if we start with a meaningful current, then we can find the value of different resistors. Once we find the resistances, particularly input resistance, from that you can find what will be the corresponding C1, because if I combine these two, namely 1 by R in into C1, the first coupling capacitor. So, that gives us the lower cutoff frequency, and on the other hand C2 typically we may take in the same order of C1. So, that signal can propagate from the output node, drain node to the subsequent stages. So, this may be clear once we cover the frequency response of the amplifier. But yeah, this is what the guidelines we should follow. If the lower cutoff frequency is given to us, typically we may target say 10 maybe 10 hertz. So, we can convert this 10 hertz into radian, and from that you can find what will be the corresponding C1. Its value may be coming in the range of microfarad. So, we have discussed these guidelines through this numerical exercises. Yeah, I think that is all to cover now, and in the next session we will be moving for the frequency response. Yeah, thank you for listening.